I've only heard back from two of you about doing a live Zoom thing today. I'm going to just go ahead and record some things for the next chapter. I think that we're in chapter, I want to say 5, 6, somewhere in there. We'll check on that here. Looks like, yeah, so we're in chapter 6 at this point. We'll get started on this. We might even finish it up today. Shouldn't be too hard, but anyway, I will connect with you tomorrow, Wednesday afternoon at 3:30 by Zoom. I should be able to do that without any trouble. And then we'll be back next week. I think we should be back next Monday. So, anyway, we're doing circular motion today. We'll start off with rotational angle, angular velocity, and move on from there. To move into circular motion, we do need to kind of switch paradigms here, stop thinking linearly so much, start thinking about a rotation angle, for example, and other things related to that. So we imagine ourselves in this rotational plane or this spinning plane instead of a standard rectangular coordinate system. And instead of talking about distance and x, distance and y, we'll talk about things like angle, delta theta. We'll use the Greek letter theta for angle. And we know from the definition of pi, actually, that the arc length of or the distance along the edge of a circle as you sweep out some particular angle, this is called the arc length of this angle. We know that that is related directly to the radius if we use a certain method for measuring, or a certain unit system, I guess, for measuring the angle. And that it's not really a unit system technically, it's a unitless unit, it's sometimes called. But anyway, a unitless measure. It is this ratio between the radius of a circle and the circumference of a circle, which happens to be 2 pi. Right? So for a full circle, we say that there are 2 pi radians of angle. And for just a small portion of the circle, it's, some number times pi radians, or just some value of radians. It could be 0.57 radians or something like that. Of course, 2 pi radians is a weird number because pi is 3.14 and 2 times pi is 6.28. So there's a total of 6.28 radians, we call them around here. And that all comes from the definition of the circumference of a circle, or the definition of pi, I suppose is the better way to say that. And it seems weird at first, but it's really just a new way of measuring. I mean, it's not really any weirder than using 360 for the number of degrees in a circle. That's all kinds of crazy in its own way. It's why 360? Well, the reason is because I think it was the Egyptians or something had like a hexadecimal or hexadecadecimal or whatever they call it. Number system, which is just a crazy number. It's the same reason we have 60 seconds in a minute and 60 minutes in an hour. It's just a weird system. We still use them because we've always used them. Napoleon tried to change all that, and others since him have, but they only managed to change measures and length and things like that. And it wasn't until scientists decided they needed a better way of measuring angle that they decided to change from 360 to 2 pi. Scientists and mathematicians saw the value in that fairly early, actually, so it stuck. But anyway, so the first thing you want to do actually is break out your calculator and change the angle setting from degrees to radians, because we will use radians a lot now. And the first relationship to remember, or to understand at the very least, is that this arc length, which we call delta S, is equal to the angle that is swept out to make that arc, delta theta times r, or delta theta equals delta S over r, either way you want to say it. And of course, if you go around all 2 pi radians of that circle and multiply by r, then you will get 2 pi total angle. Here they have a table of comparisons between degrees and radians for 30, 60, 90, 120, 135, and 180 degrees. And so on. So there you have your conversion factor, right? Your conversion factor is right here from radians to degrees or degrees to radians. And then the next thing we want to do is we want to talk about how fast something might be rotating. So the amount of angle every second, and we call that angular velocity. And it is going to be delta theta over delta t. The interesting thing about this situation is that we have this relationship between the distance or the arc length along the edge of the circle and the angle, and that's this relationship here. But now we have delta theta over delta t, and if we put the relationship in for delta theta right here, we get a relationship between the angle and the velocity of the particle along the edge of the circle. It's not a linear velocity, and technically it's not really a velocity. It's also often called a tangential velocity. It's a constantly changing velocity. So I guess it is a velocity, but it's just not a constant one. But it's changing all the time as it goes around because the direction is changing. Even if the actual magnitude of the velocity doesn't change, the direction is changing because it's turning. And so it becomes a fairly unique velocity for us here. And so here they do this relation. They do this substitution where they substitute in s equals r times delta theta, delta s equals r times delta theta into this equation, and they get but they also talk about this tangential velocity or the speed along the edge of the circle being delta s over delta t. And when they plug the relationship in for delta s into this equation, they get r delta theta over delta t, which is r times omega, because omega is defined as delta theta over delta t. And there's many ways you can do this. The end result is most important. What we learn here is that there is a relationship between the speed along the edge of the circle, which is this v, and the angular velocity at the center of the circle, which is omega. You multiply by the radius, and you multiply the angular velocity by the radius, and you get the tangential velocity, which is the speed along the edge of the circle. And of course, that can be arranged to solve for different things. But that's a very important thing to recognize, to realize. The reason that this is important is because when you have something like a rolling disc or a rolling wheel or a rolling ball or anything that is rolling without slipping, in other words, the edge of the circle is moving at the same tangential velocity as the object is rolling forward linearly, then you can relate now that linear velocity to that tangential velocity. And that becomes quite useful. So that becomes quite useful in a situation like this.
You didn't close the door.
I got it.
Thank you.
So here's an example. We have the angular. We're going to calculate the angular velocity of a car with a tire 0.3 meters radius when it's moving at 15 meters per second. So because we've been given the linear speed of the car moving forward, we can say that that linear speed moving forward is going to be the same value or the same magnitude as the tangential velocity along the edge of the tire. As long as the tire is not slipping as it rolls along the road or skidding as it rolls along the road, then like a fly moving along the edge of this tire would be moving at the same speed as the car is moving forward. And so we can make that, we can include that in our equation. So the linear speed of the car, 15 meters per second, becomes the tangential velocity along the edge of the tire, 15 meters per second. Tangential velocity along the edge of the tire is equal to the radius of the tire times the angular velocity of the tire. We solve it for the angular velocity of the tire, and it's that simple. It becomes 50 radians per second. Now, does that make sense? 50 radians per second, 50 radians, radians, there are 2 pi radians per rotation. 2 pi is about 6.28. So this is starting to look something like, a little bit less than 10 rotations per second, maybe 8 rotations per second. Does that make sense? As you see a car go by, can you imagine that tire is rotating 8 times around every second? And, at a fairly decent velocity, yeah, you can imagine those tires going around 8 times per second. At higher speeds, they're definitely going around faster than that. So that's a good number that makes sense to us. And then we have to talk about what it is that actually keeps this thing traveling along that edge of that circle. We have to understand what this motion is, what's happening here. So we're going to look at 2 different points along the edge of the circle, point B and point C, and we're going to essentially calculate the acceleration or the change in velocity. Here's the velocity at point B. It's pointing a little bit upward, well, a little bit to the left and mostly upward. And this at point C, velocity 2 is pointing mostly to the left and just a little bit upward. They have the same magnitude, the same length, same speed, essentially, just different directions. But as they move from one point to the other, there's an acceleration, which is defined by the change in velocity. The change in speed is 0. It's not changing speed at all, but it is changing direction. And so we figure out the change in direction by putting these 2 things tail to tail and taking their difference, going from the first to the second. And we see that change in velocity is actually pointing towards the center of the circle. If we take the average right here in the middle, that average change in velocity is going to be in the same direction as the acceleration and actually equal to the acceleration of the particle. So we learn that this particle is actually accelerating towards the center of the circle. That center pointing acceleration is what we call the centripetal acceleration. Centripetal literally means center pointing, center seeking. So that's what we call the centripetal acceleration, not to be confused with the centrifugal acceleration. Centrifugal acceleration is something we'll talk about later. So here they do the kind of the math of that vector thing that we did up above. And the interesting thing here is they're again using some of these relationships that we know. We know that, for example, delta S over delta T is the speed along the edge of the circle, or the tangential velocity, it could be thought of. And they go through some math and they get to this point where we actually find the value of the centripetal acceleration's magnitude. But this is only good because the way that we've done the math up here is using kinematic equations with constant velocity along the edge of the circle, or constant speed rather, not constant velocity because it's not the same direction all the time, but the constant speed along the edge of the circle. And when you do that, you get a result that looks like this. The centripetal acceleration of an object that's moving along the edge of the circle at a constant speed is that speed squared, which we use v for speed. I know it gets a little confusing here, but we use that linear or tangential speed along the edge of the circle squared divided by the radius of the circle. And that tells you the acceleration that particle is experiencing. And that is, quite literally, the acceleration that keeps it on the edge of the circle. That's what's causing it to turn so that it's moving in a circle. And if we use our relationship between tangential speed and angular velocity, that will get us to this equation here, where the centripetal acceleration equals the radius times the angular velocity squared, the magnitude of the angular velocity squared. And either of these will give you the answer that you need. Notice here again that we had previously we discovered 2 different things that were relating kind of these quantities along the edge of the circle and quantities of angle. And here are those. Let me write them down for you really quick. I don't have my drawing tools out because I'm not using Zoom. That's okay. The 2 previous ones that we had were we had let's see, we had the arc length is equal to r times theta, right? So we have this r present in there that does this conversion from kind of the motion along the edge of the circle to the motion in the center of the circle. And then with the angular velocity, we found that the tangential velocity along the edge of the circle is equal to r times the angular velocity. So r is there as well. And here we have centripetal acceleration equals r times omega squared, or v squared over r. R is always present there. R is kind of this, the radius of the circle that you're traveling on, plays a role going from the angular part of the motion to the on the edge of the circle kind of motion, the tangential motion along the edge of the circle. So we're going to use this new equation that helps us to calculate the centripetal acceleration, and we're going to calculate the acceleration of going around a curve coming off the freeway, for example, to the acceleration we feel because of gravity. So here we're going around a curve that at 25 meters per second of tangential velocity, the curve has a 500 meter radius, and we calculate v squared over r gets 1.25 meters per second squared of centripetal acceleration. Of course, gravity is 9.8, so this is, approximately 1/6 of that, or something, 1/7 or something like that. An ultracentrifuge is a device that's designed to spin chemicals. They spin the chemicals so that they can separate the more massive precipitates from the solution in a chemistry experiment. And so they put them in this device, and they put these vials of things in this device, and it spins around really, really fast, like insanely fast, actually. And as it does that, the precipitates fall to the bottom, or we say that they fall to the bottom. Of course, they don't fall to the bottom. They're actually, as these things spin around, they're trying to continue going forward, and then the bottle turns and gets in their way, so they actually end up running into the bottom of the vial. But it's neither here nor there. But the point is that the centripetal acceleration of this can be calculated. It has a radius of 7.5 centimeters, so that'll be 0.075 meters. And the ultracentrifuge is spinning at 7.5 times 10 to the 4 revolutions per minute. Now, we haven't used revolutions per minute here yet. Revolution per minute is often shortened to RPM, but a revolution per minute means that it goes around once every minute. And in this case, it's 7.5 times 10 to the 4 times every minute. That's a lot of revolutions per minute. But we need to convert that into amount of angle in radians per second instead of revolutions per minute. So we have two conversions to do: convert revolutions to radians and then convert minutes to seconds. And this is how they do that: 7.5 times 10 to the 4 revolutions per minute times 2 pi radians per revolution, because there are 2 pi radians for every time you go around. And then times 1 minute every 60 seconds. Here we're going to cancel out the revolutions. We'll get radians per minute. Here the minutes will cancel out, and we'll get radians per second. And it turns out to be 7,854 radians per second, which is a little bit over 1,000 revolutions per second. Let's see here. Oh yeah, now they're going to calculate the centripetal acceleration. So r times omega squared. R converted into meters, the omega here squared, gives a huge amount of acceleration, 4.63 times 10 to the 6 meters per second squared. Much more acceleration than the human body can handle. In fact, not many things at all can handle that kind of acceleration. They're just accelerating a liquid and a precipitate, so it's nothing to worry about, but that's a lot of acceleration. And of course, once you have an acceleration, we can use Newton's second law to determine a force, because force equals mass times acceleration. So the centripetal force is the force that causes that centripetal acceleration, and centripetal force equals mass times centripetal acceleration. And we can actually replace the centripetal acceleration in this equation with one of the two formulas that we have for centripetal acceleration and get centripetal force equals mass times tangential velocity squared over r, or centripetal force equals mass times r times angular velocity squared, those being all magnitudes of those quantities. You can also solve for the radius. Radius equals mass times tangential velocity squared over centripetal force. In this particular case, if the mass and the speed of the mass remain constant and the centripetal force is constant, then of course the radius will change. If the mass and the velocity squared stayed constant and the centripetal force does not stay constant, then the radius will change. As the force goes up, the radius will go down, and as the force goes down, the radius will go up. If the velocity squared and the force centripetal force stay constant and the mass changes, then as the mass goes up, the radius will go up, and so on. As the mass goes down, the radius will go down. The same for the velocity. If the velocity is the thing changing and everything else is staying the same, then r changes directly with the radius as well, and that's what they're talking about here. Now we can use this to determine how much friction tires need between the road and the tire as it's turning on a flat curve. And the way that we do it is we say that the friction that holds the tires, keeps the tires from slipping, is the force that is pushing the tires so that the tires go around this flat curve. So we say that the centripetal force, which equals mv squared over r, and here are the numbers that they've given us for that. They have a mass of a car, they have the speed of the car going around the turn, and the radius of the turn. So they have that centripetal force and they calculate it and write it out here. But then they let this force, which is the centripetal force, equal the friction force. And of course the friction force equals the static coefficient of friction times the normal force. And the normal force on a flat curve is just the weight of the car. So this becomes the weight of the car here. And of course you can set this equal to this one and then solve for this static coefficient of friction, which is what they do. They solve it here, and what we find out is that it doesn't even depend on the mass of the car in the end. The mass of the car is on both sides of the equation, so it cancels out. And it really only depends on how fast you're going and what the radius of the turn is. It also depends on gravity, but gravity doesn't change much along the Earth, so we don't worry about it. When we start driving cars on the moon, we'll have to worry about that. But so anytime an engineer is designing an off-ramp or on-ramp on or off a freeway or something, or just a turn in a road or whatever, and they're making a flat road, they use this equation. They say, well, how fast are the cars going? That's your V. And then we know the static coefficient between the road and the tires is standardized, because that is standardized for cars. They want that friction to be the same at a certain number or better for all cars, and then you solve for the radius of the curve, and then you build the curve of that radius or whatever. Or if you don't have a choice of how big you're going to build it, because maybe there's a mountain in the way or something else, and you have to build this curve a certain size, then you put the r in at that certain size, it's the static coefficient of friction in here, and you solve for how fast the car should go around the curb, and you put up a sign and say, go slower than this speed or whatever. Very useful. Here they're going to actually calculate for the static coefficient of friction at 0.13. So, and you want, of course, your tires to have much higher static coefficient of friction than that, because why take chances, right? And this is what that free body diagram would look like for the car turning on a flat curve. You have the weight of the car down, which equals the normal force up on this horizontal surface, and that means your static friction is mu s times n, which is mu s times w, essentially. And then that has to equal the centripetal force right there, which is equal to mass times the centripetal acceleration, and that's how they get there. And here they show kind of in detail how we get from the point that, I got ahead of myself there. So that previous example was for a turn on a flat surface. So going around a curve on a flat surface. But many times cars go around and they're going around a banked curve, a surface that at some angle. And they actually go through in great detail how to calculate, for example, the ideal angle for a particular velocity right here in a radius of a curve here. They go through this in great detail. Where this is your free body diagram, your weight is straight down and your normal force is now perpendicular to the surface that you're on, which is at some angle, whatever it is, theta. And only part of the weight is actually, the weight here is essentially doing two things. The weight is going to cancel out part of the normal force, but the other part of the normal force, the part that's pushed, so the part of the normal force that's going straight up will be canceled out by the weight, but the part of the normal force that's pointing this way, because it's, tilted slightly to the left, that component of the normal force is actually pointing towards the center of this turn. So it's pointing towards the center of the circle. That right there, that little component of this normal force is actually going to be our centripetal force. So here they show that. They say that the normal force times the cosine of theta, which is this component of the normal force, is equal to the weight. It's equal to this. But this one right here, which is the normal force times the sine of theta, is equal to the centripetal force, which is equal to, of course, the mass times the centripetal acceleration. And then they do that example here where they actually calculate the angle, and they take this math that's been done here. It's quite, this right here comes from that last thing that I said, that the normal force times the sine of theta equals the centripetal acceleration. So centripetal acceleration equals mass times velocity squared over r. And then you can solve this equation, the normal force being mass times gravity, so mass times gravity comes over here. And then they do something they do something a little bit weird. They take the other equation, which is n cosine theta equals mg, and they actually divide this first equation by this second equation. So they end up with not just sine theta, but sine over cosine, and you still have m on both sides, but it cancels out because you can divide it off both sides. And then you end up with this equation where the tangent of theta is equal to v squared over rg. Well, we're going around at a constant speed, so v is a constant. The radius of the turn is constant. G is a constant. That means all these numbers are constants, and we can solve for theta. And we do. We solve for theta, the ideal angle for turning around a bank curve. Now this doesn't include friction. Notice that we don't have, static friction or any kind of up here on the flat turn we had friction, but on this banked turn we don't have any friction. It's just the normal force, the weight, and this leftover component of the normal force that didn't get canceled out by the weight, because this one gets canceled out by the weight. This one doesn't get canceled out by the weight, and that's the thing that becomes the centripetal force. So you don't like use up any tire rubber when you're going around a turn like this, because you're not creating any friction. It's not going to heat up the tires and make the rubber evaporate. It's not going to skid any hot rubber onto the concrete or whatever. It's actually the bank of the turn, or the angle of the road, that turns the car, not the actual friction between the tires and the road. And that's why they bank the turns on racetracks. If a NASCAR driver, for example, is very smart and has planned out his race very carefully, he can turn corners without losing very much tire mass, because he's at the perfect radius, at the perfect speed, and on this turn that is at a particular angle. And if you have just the right speed going around that turn of a particular angle at a particular radius, the turn will turn the car. The actual road will turn the car, not your tires. So you save tires, you have to pit stop less, and you win. So here they just calculate that. They calculate the velocity of a particular curve with an angle theta and a radius r, and so you have to rearrange the equation and solve for r, or solve for v here, and they do that. And of course, this is again something that's done quite a bit in city planning and other things like this, highway planning, highway design. And I think I'm going to go ahead and leave these last three for next time. I keep getting people in and out, so I'm not sure that this is going to be a great video. But I'm going to leave it for this. Leave it at this point, and let you guys go ahead and start the homework on your own, and we'll get finished with this on Wednesday. And if there are any questions that you have, please feel free to email me, and I'll post this on YouTube ASAP. Have a good one. Bye.